In this lesson, we continue with some examples of practical applications that lead to functional equations. We combine the theory and the practice to make it more enjoyable and to motivate the students. Our first equation is the translation equation, which arises in a natural form in the problem of damage accumulation, as we will see later. The general solution of the translation equation is given here, in which it appears an invertible function of a single argument function phi. Some important assumptions must be made for the f function, as for example, the strict monotonicity with respect to its second argument. It is interesting to connect the mathematical properties of the function with their physical meaning, as we will see in the examples following. The first relevant conclusion is that the two-argument function cannot be given arbitrarily. On the contrary, the only degree of freedom we have is a one-argument invertible function phi, which means a very high restriction with respect to the degrees of freedom of the function f appearing in the functional equation. As in previous functional equations, we can ask ourselves about the uniqueness problem of the function phi. The answer to this question is contained in this theorem, which shows that we have uniqueness up to a translation, represented by the constant c. As before, our lemma of a previous lesson allows us to demonstrate the theorem result. Our next example is the case of damage accumulation curves. These curves provide the fatigue cumulative damage after a specimen is subject to a given load for a given number of cycles. More precisely, damage accumulation curves represent how the damage increases as a function of the number of cycles n under constant load. These curves are used to derive the damage accumulation rate curves to be applied in engineering design. Next, a damage accumulation model is derived. As usual, we start from observing damage accumulation experimental results, and we try to use no arbitrary assumptions or lightly restrictive assumptions.
Let me now explain you how to use functional equation to calculate the damage curve of a fatigue model. In this case, we want to know how the size of the crack increases with the number of cycles. I subject a piece to a cycle load, and then I want to know how the crack size increases with the number of cycles.
Thus, the different behavior of specimens is due to the random initial crack size, which is illustrated by the corresponding probability density function of the random crack sizes at the initial stage and the applied stresses. Next, we derive a model for the deterministic damage accumulation curves, which means that the specimen, the initial damage and the load are known. It is, they are deterministic. From the previous figure, we can draw the following conclusions, which are relevant to our model. First, damage accumulation curves are concave from above. Second, the damage accumulation curves depend on the initial damage. Third, the different damage accumulation curves follow similar patterns, which appear to depend only on the initial damage and the applied load. Thus, given the specimen, the initial damage and applied load, this curve can be assumed to be deterministic. 4. If the load and or the initial damage are modified, different sets of curves are obtained. Note that the larger the load or the larger the initial damage, the smaller the specimen lifetime. In this lesson, we derive a model for the deterministic damage d as a function of the initial damage d0 and the number of cycles or lifetime n, assuming that all of them are deterministic and that the load remains constant during the testing process. We use an asterisk to refer to a dimensional or dimensionless radius, as suggested by the Buckingham theorem.
What I look for is for a function h that, given an initial crack size and a number of cycles, will give me the final crack size. So I start with a crack size h0, and because I subject this to fatigue cycles, to n fatigue cycles, then I get a larger crack size, which is a. And I want to know how this function h is. But this function has to satisfy some consistency condition that is very important. I should get the same if I start from a crack size a0 and I use n1 plus n2 cycles, that If I first apply N1 cycles and I calculate the new crack size, which is used as an initial size for the second step with N2 cycles. If I write this condition, I get the functional equation that you have there, and you can see that this functional equation is the well-known translation equation that has as the only solution the one that you see there. It is interesting to see that we were looking for a function h of two arguments, h0 and n. And now we can write this function with only one function of one argument. That is, the model is much simpler than we expected. And functional equations tell us that the phi function has to be invertible. So this is a very interesting result.
If the inverse value of d0 by function phi is null, we get that the damage d is equal to phi of n. That is, we can now understand the real meaning of function phi that gives the damage after n cycles when the initial damage d0 is considered associated with 0 cycles. To see if the phi function is unique, we can solve the indicated uniqueness functional equation. We assume that there exist two functions phi1 and phi2 that provide the same damages for all possible combinations of initial damage d0 and number of cycles n, and conclude that the two functions must be related as in the box expression. In other words, apart from a translation of value b, we have uniqueness. Our damage accumulation formula in the slide suggests the following method to obtain the crack size d for a given number of cycles n, which is illustrated in the figure in red color, together with another crack growth curve in blue color, coming from a translation of the previous curve and providing exactly the same values. It is interesting that our damage accumulation model allows us to obtain the number of cycles required to get a given damage level when we start from a given initial damage d0, and also the initial damage d0 from where we must start to get a cumulative damage d after n cycles. This permits obtaining the number of cycles n required to go from an initial damage d0 to a cumulative damage d, and also recovering the initial damage d0 from the damage d and the number of cycles n. In summary, the solution of our functional equation provides the most general damage accumulation model for a constant dimensionless load in terms of an arbitrary invertible function phi, and shows the relation between lifetime n, initial damage d0, and crack size d after n cycles, allowing us to develop a closed form expression of either of them in terms of the other two variables, once the function phi is known. Our next example is the case of a stress-strain law, which appears very frequently in the strength of materials field. We look for a stress-strain law providing the stress resulting after application of a stress delta sigma when the initial strain is epsilon 0. We assume that the resulting strain is independent of the way the stress level delta sigma has been reached. This condition means that if we apply a stress delta sigma 1 first and later delta sigma 2, we must obtain the same resulting strain as if we apply delta sigma 1 plus delta sigma 2 at once. That is, the indicated translational functional equation holds. Fortunately, we already know the general solution of this equation and can write it below. Note that our initial problem of finding a two-argument function f reduces now to a single argument function phi, that is, it is greatly simplified due to the translation property use. If further we force the strain to be of the form in the top equation, replacing it into our functional equation leads to a Cauchy functional equation, and using the form of its solution, we finally demonstrate that the only possible solution is the linear model. Now we change topic and move to geometry to derive the well-known Euler formula for polyhedra. The Euler formula for polyhedra at the top of the slide expresses that the number of faces f of a polyhedron is equal to the number of edges e minus the number of vertices b plus 2. Two simpler examples as the tetrahedron and the cube obviously satisfy this equation, as the reader can check immediately. Our purpose is to characterize next this formula using several systems of functional equations. We assume that there is an unknown expression that gives the number of faces f as a function of the number of edges E and the number of vertices V of the polyhedron. To derive some functional equations to be satisfied by the Euler formula, we perform short perturbation of a polyhedron such that it is transformed into another polyhedron with different number of faces, vertices, and edges. Our first perturbation 1 consists of a truncation of one vertex with X intersecting edges. The figure shows two polyhedra with E1, F1, B1, and E2, F2, V2 edges, faces and vertices respectively, where the second one comes from the first after truncating one vertex with X intersecting edges. That is, we have the indicated relation between these elements for the initial and the resulting polyhedra. As we apply the function f to both polyhedra, we must have the functional equation at the bottom of the slide. To solve the functional equation, which has been repeated at the top of this transparency for convenience, we first let E equal to E0 and call H of S minus R, F of R and S. Make Y equal to V minus E0 and replace into expression 10 to obtain a difference equation in terms of V minus E0, or to simplify in terms of Y. Since it is a difference equation in function H, its solution is the one shown in the box expression, where K is an arbitrary constant. Next, replacing this into expression 11 leads to expression 13, which together with the formula for any particular simple polyhedron, for example the case of a tetrahedron, provides K equal to 2, that is the Euler formula. Our perturbation 2 consists of adding an X plus 1 face polyhedron to another polyhedron, as illustrated in the figure. The reader can check that the indicated relations between the faces, vertices and edges of the two polyhedra hold, and then, applying function f to express the number of faces of both polyhedra, we get the functional equation at the bottom of the slide. To solve this equation that has been repeated at the top to facilitate things, we make x equal to y and x equal to y plus 1 and get the indicated system of equations. And subtracting both equations and calling p to e1 plus y and q equal to v1 plus 1, we get the indicated difference equation 15, whose general solution is that in 16, where c is an arbitrary function, an arbitrary constant. Next, substitution of 16 into 14 leads to the difference equation in 17, whose solution is given in 18, where k is an arbitrary constant. Thus, replacing this into 16, we get expression 19. As before, this together with the formula for any particular simple polyhedron, for example the case of a tetrahedron, provides k equal to 2, that is the Euler formula. Our perturbation 3 consists of joining two polyhedra with a common face. When joining two polyhedra with a common face, as illustrated in the figures, the number of faces of the new generated polyhedron depends on whether the two faces sharing one edge of the initially common face are coplanary. This dilemma exists for every edge of the common face. So, if we call C to the number of coplanary occurrences and X the number of sides of the common face, we get expressions 20 for the number of faces, vertices and edges of the resulting polyhedron, which lead to the functional equations given in 21. Note that both right-hand sides of 21 imply the same solutions. Note that the first comes from the second by substituting x by x minus 1. Perturbation 3a. Joining two polyhedra, case of 0 less than c less than x. In this case, to solve 21, we make c equal to c0 and c equal to c1, and we subtract both to get the indicated expression. Next, if we call p, q and h0 to the given values, we get expression 22, whose general solution is the one in 23, where g is an arbitrary function. Next, replacing 23 into 21 and making x equal to x0 and letting h of u be the indicated expression leads to the Cauchy equation 1, and 23 becomes expression 25. Finally, substitution of 25 into 21 gives alpha equal to minus 1/2 and beta equal to 3, that leads to the Euler formula. Perturbation 3b, joining two polyhedra, case C equal to 0. This is the case of perturbation 3 with C equal to 0, which leads to the equation 26 and making x equal to v1 plus v2 minus k and x equal to k with k constant, we get the system of two equations in this slide, from which we get equation 27, which implies 28. Entering 28 into 26 and calling x equal to e1 minus v1 and y equal to e2 minus v2 gives the modified Cauchy's equation with indicated solution. Then equation 28 gives expression 29, which together with the formula for any particular simple polyhedron, for example the case of a tetrahedron, provides alpha equal to 1 and the Euler formula. In this slide we present our final results. We shall prove that equations 9 and 26 or equations 14 and 26 characterize the Euler formula. Since equations 9 and 14 have the same general solution, they are equivalent. Thus, we only demonstrate the first case. Taking into account that the general solutions of the functional equations 9 and 26 are 19 and 29, the general solution of the system 9 and 26 is given by the solution of the functional equation in the slide, which implies the equation on the right. Finally, alpha equal to 1 and k equal to 2. Thus, the general solution of the system 9 and 26 becomes the Euler formula for polyhedra. Then we have characterized the Euler formula by 5 different forms, that is, equation 21, system 9 and 26, system 14 and 26, and systems 9 or 14 together with the formula for any particular simple polyhedron. Our next application refers to iterative methods and associated functional equations, which are very interesting and suggest many applications. We deal with the theory of continuous iteration of functions. First, we see that the iterative method satisfies the translation functional equation, whose solution we already know that it is the one in expression 30, which for n equal to 1 gives the function f in terms of the g function. It is important to realize that given any invertible one-argument function g, equation 31 gives us the function f. However, the problem of obtaining gx from f of x is more complicated. Our first example is a linear example in which the g function is the one given at the top of the slide. To obtain the nth iterate from 30, we need the inverse function of g, which can be obtained from 32, making this expression equal to u and obtaining x as a function of u to get the expression 33. Now we replace g and its inverse into 30 and get 34. Finally, with n equal to 1, we obtain the function f at the bottom of the slide. Our second example is a nonlinear example in which the g function is the one given at the top of the slide. To obtain the nth iterate from 30, we need the inverse function of g, which can be obtained from 35, making this expression equal to u, and obtaining x as a function of u to get the expression 36. Now we replace g and its inverse into 30 and get 37. Finally, with n equal to 1, we obtain the function f at the bottom of the slide. Our next application is to functional networks.
Now, assume that we are a medical doctor, I am a medical doctor, and I want to know the probability of a given disease when a patient has symptoms X, Y, and Z at given levels. So I want to calculate the probability of the patients to have the disease if I know the values for these symptoms X, Y, and Z. What I can do is, first, I can combine the symptoms X and Y, extracting the information these two symptoms have on the disease by a function g. So g of xy means the information that these two symptoms have on the disease. And then I combine this with the C symptom by a function f. And finally, this f function gives us this probability. However, you can see that instead of starting by x and y, I can start with y and z and extract the information these two symptoms have on the disease by an n function, And then combining with the first symptom with the K function, I can obtain the same probability. Finally, I can do the same with X and C and then with Y. So what I get is two equations, because I have two equality signs there.
Thus, the probability Q of the patient having the disease can be calculated by means of a function of any two symptoms, a summary of the influences of symptoms, and the influence of the remaining symptom C. In other words, we must obtain the same probability Q using the following three methods. First, combining X and Y by function G and then using function F with this value and C. Second, combining Y and C by function N and then using function K with X and this value. And third, combining X and C by function M and then using function L with Y and this value. If the variables measure symptoms which are directly related to the disease, it is reasonable to assume that the function f, k, l, g, n, and m are invertible, strictly monotonic with respect to both variables. This means that the higher lower level of one symptom, the higher lower probability of the disease.
And I have 6 unknowns, f, g, k, n, l, and m, which are functions of two arguments. So I have a system of two equations with 6 unknowns.
This network is not a neural network, but a functional network because, first, the neural functions are arbitrary. Second, the neural functions are multi-argument as f, g, k, l, m, and n. Third, the outputs of neurons f, l, and k are coincident, that is, leading to the same output u. Thus, neural networks are clearly inappropriate to reproduce this model. The coincident connections in unit u, or equivalently the functional equations 38, put strong conditions on the neural functions f, g, k, l, m, and n. The general continuous solution of the system of functional equations 38 is in 39, where k, g, p, and q are arbitrary functions and f, m, and n are arbitrary invertible functions. Replacing this into 38, we get expression 40 that suggests as a simplified functional network equivalent to the initial one. That suggests as a simplified functional network equivalent to the initial one. Note that the network topology and the functional structure of the functional network associated with 40 is much simpler than the one associated with 38.
This is a graphical illustration of the method. The I means identity, and the G, M, L, N, K, etc. are the functions that we used before. This represents a network in which you put the symptoms X, Y, and Z, and you get U as the probability of the disease. But this initial network can be greatly simplified by the other one, which is equivalent to that one, and in this one we have only 4 functions of a single argument. So using functional equations we have been able to simplify the problem.
In this lesson, we have seen several functional equations, for example, the translational equation, which was used to find a Kraft-Grove model, and 2 iterative methods. We have also obtained the Euler formula for a polyhedra and some applications to artificial intelligence. With this example, we suggest you to think on possible application to your own field of specialty. I invite you to follow the next lesson dedicated to some methods to solve functional equations, in which we explain how to solve functional equations. We inform the reader that it is not easy to find explicit methods for this purpose.